Hi, this is a presentation on continual learning from the perspective of compression. This is a joint work with Liming from Mila. In this work, we study the problem of catastrophic forgetting and continual learning using the theory of minimum description length. According to this theory, when we compress a data sequence x1 to xn using a model with parameter theta, the description length of the data has two parts. The first part is the description length of the data encoded with the help of the model. The second part is the description length of the model itself. To compute the first part, we can use the so-called Shannon final code, which says that the description length of x given theta is the negative log probability of x given theta. To compute the second part, which is the description length of the model itself, we can use the Bayesian mixture code. As we can see here, the log probability of the data can be lower bounded by the evidence lower bound elbow, which has two parts. The first part corresponds to the description length of the data encoded with the help of the model. The second part is a KL divergence between the posterior and the prior, which corresponds to the description length of the model itself if we use B-spec coding. According to MTL, the best model that explains the data is the model that achieves the minimum overall description length of both parts. Another method that computes the description length of the entire data sequence without explicitly compute the description length of the model is to use the so-called prequential or online code. Prequential here stands for predictive sequential. The idea behind this code is to rewrite the log probability of the data sequence as the sum of log conditional probability of each observation given previous observations. In this way, the problem of compression is turned into a problem of predicting the next data. This can also be viewed as an autoregressive model. The key for this code is to use a prediction strategy that predicts the next observation based on previous observations. For example, the Bayesian mixture code uses the following prediction strategy. Another example is the maximum likelihood plugin code, which uses a prediction strategy based on a parametric model with parameter theta, where the parameter is trained by maximizing the likelihood of previous data. Using the theory of MTL, we propose an information-theoretic definition of forgetting in order to measure forgetting in a principled way. We saw before the description length of the data can be divided into two parts, where the description length of the model is only one part. This means that the model itself is not enough to recover the data losslessly. We also need the encoding of the data, which can be considered as the information not captured by the model. Therefore, if after changing the model parameter, the description length of the first part increases, then the model has forgotten more about the data. This motivates us to provide the following definition about forgetting. The amount of forgetting about theta x caused by changing the model parameters from theta I to theta j is the difference between the description length of x given theta j and the description length of x given theta I. We threshold the difference at value 0, since when the description length does not increase, there is actually no forgetting. Many continual learning methods have been proposed to overcome catastrophic forgetting. There are several paradigms emerged from these methods. The first paradigm can be represented by variational continual learning, VCL. In such paradigm, the methods apply variational method to approximate a parameter posterior and online update posterior using the Bayes rule. Another paradigm is represented by deep generative replay, or DGR. In such methods, people usually learn a generative model of past data, and new data are learned together with the samples of the generative model. From the perspective of compression, these two methods can actually be considered as approximations to two prequential coding methods that we discussed before. For example, VCL can be considered as a continual learning approximation of Bayesian mixture code. As we saw before, the Bayesian mixture code uses this prediction strategy, where the term in the red box depends on the data from previous steps. Since in continual learning we do not store all previous data, this term cannot be computed exactly. So VCL approximates this posterior p by a parametric posterior q. Since by Bayes rule, the posterior p can be written recursively as a term that uses posterior from the previous step. VCL can therefore recursively update q by minimizing the KL divergence between q and the term that used the previous q at t-1. Deep generative replay, on the other hand, can be considered as an approximation to the ML plugin code. The ML plugin code, as we saw before, uses this prediction strategy, where the parameter theta is optimized by maximizing the likelihood over previous data. And since we do not store previous data in continual learning, deep generative replay therefore approximates this term by a expected log likelihood using samples from the generative model. And therefore, the parameters of the generative model can be recursively updated by, at each step, maximizing the log likelihood of the current observation and a expected log likelihood using the generative model. In our paper, we also measured forgetting and compression of the two prequential coding methods and their continual learning approximations. In the left figure, we can see that the two prequential coding methods, ML plugin and the Bayesian mixture code, have almost zero forgetting, as they store all previous data, whereas their continual learning approximations, replay and VCL, have lower forgetting than the catastrophic baseline, but higher forgetting than the prequential coding methods. And between these two approximations, VCL has much more forgetting than replay. On the right side is a figure of prequential code lengths of different methods. And as we can see that ML plugin achieved the best performance in this case, whereas VCL achieved the worst performance. In our paper, we analyze the limitations of VCL and explain why it achieves the poor performance. If you're interested, please read the details in our paper. To address the limitations of VCL, we also proposed a method called ML mixture code. The performance in terms of forgetting and compression of ML mixture code are also presented here. The ML mixture code can be considered as a combination of ML plugin code and the Bayesian mixture code using a hierarchical model, where the metaparameter phi is learned in a maximum likelihood fashion similar to ML plugin code, and the parameter theta is given by a parametric distribution using metaparameter phi similar to Bayesian mixture code. In order to apply this method in continual learning, we developed a recursive loss of the metaparameter phi that does not depend on previous data. The idea is to divide this loss function phi at time t into two parts, where the first part is simply the loss function at the previous time step, and the second part in the red box can be further divided into two terms, where the first term corresponds to a maximum likelihood loss on current data t, and the second part is a KL regularization that prevents forgetting. It's not hard to see that this recursive loss function has similar computation cost to VCL, and as we saw before in two figures, is better at preventing forgetting. With this, I come to an end, and thank you for your time and attention.